going to be talking about how we can derive some useful bounds on various properties of cognitive and conscious agents by considering them in rather extreme physical conditions. This is essentially an overview of undoubtedly the most cursed chapter of my PhD thesis, so yeah. So how can we characterize something so abstract as consciousness, like in general? There are obviously a number of different schools of thought, no pun intended, we can defer to, such as neuroscience, philosophy, psychology, and so on. However, I decided that instead of these sensible choices, I want to use mathematical physics, partially because I enjoy suffering, but also mostly because I want these as results to apply no matter what the substrate. In general, we can study problems by abstracting a concrete particular or concrete general situation to an abstract specific or abstract general situation, one which is more amenable to analysis. We can also relate it to another better known problem, hopefully one that is well understood, with the caveat that the characterization of the better known problem might not be the most satisfactory or optimal characterization for our original problem, whether in terms of actual like numerical results or just plain old insight. We can also consider how a system would react when placed in extreme circumstances. And as you can probably guess from the title of this talk, and admittedly what I said earlier, I really do mean extreme. However, we will do all three. We will consider arbitrary conscious agents in extreme scenarios and consider them as what are essentially tiny neutron stars. What could go wrong? Okay. So we'll quickly go over some background assumptions. Well, the main ones that I've identified anyway, which I'm operating under. There are four main philosophical ones and one physical one. The first assumption is that the state of consciousness requires, or rather, the ability to be conscious requires and builds upon the ability of cognition. By cognition, I really just mean the ability to have some sort of internal state that can be transformed. And here on, I'll just use cognition and consciousness interchangeably, even though, yeah. Next, we assume that cognition itself is a computational process. That is, a process which manipulates information. For our purposes, we will stick to considering classical information, as there are some funky things that can happen when given access to quantum memory. So this is left for future stuff. Further, we assume that computation happens in some vaguely mechanistic Platonic-esque realm where there is some notion of dynamics, logic, and cause and effect. The final philosophical assumption is that for this realm to be relevant to a physical universe, it requires a physical representation and projection. For example, a computer, a brain, whatever. Finally, assume that quantum field theory in curved space-time is a sufficiently accurate approximation for the energy scales and length scales that we are talking about. This is undoubtedly the biggest assumption I'm making and the least justifiable, but it's probably valid for most cases. In edge cases, it will certainly break down. However, before it breaks down completely, the results will likely be more and more quantitatively different before it eventually becomes qualitatively different. Okay, so for some background, let's start with agents. An agent is just an entity with behaviors and goals. Agents, of course, also exist in an environment. Both the agent and the environment can maintain a state, and the agent and the environment can communicate with each other in order to influence each other. This can be best understood computationally by models such as communicating Turing machines, process calculi, actor models, p-systems, and so on. It doesn't really matter what computational model you select, as long as it's universal and can be transformed into an equivalent Turing machine. Okay, so it would be nice to have a way to measure how complex some mathematically derived object is that at least somewhat aligns with our inherent notion of how complicated something is. I don't necessarily mean computational complexity either. So I don't mean in terms of like P or NP or whatever. Furthermore, out of principle, it would be nice to be able to measure this complexity without reference to other objects. So, for example, we don't want something like Shannon information. Also, we want this measurement to have some basis in computation, since we are positing that we are dealing with computational processes. So to be more specific, we want a computationally parsimonious way in which to measure the inherent complexity of an object. Well, let's start simpler. How do we even computationally describe objects? The answer is in the question. A computational description of an object is its computation. Computations certainly have multiple notions of complexity, such as the runtime or the memory used. What we'll consider is much simpler, however, the size of the program itself. One catch is that multiple computations, and this is called Kolmogorov, the Kolmogorov complexity of an object. Oh, I should have said that later. One catch is that multiple computations, that is, multiple programs, can produce the same object. So let's just take the smallest program, which produces our object, and take its size as these notes are out of order, and take its size as a measure of complexity. This is the Kolmogorov complexity of our object, measured in bits. Oh, these are really out of order. Oh no. How long have they been out of order? Okay, it's easy to show that Kolmogorov complexity is universal. Did I just say that one? Yeah, it's easy to show that Kolmogorov complexity is universal, modular, and additive constant, depending on the specific model of computation you choose. Now, extremely brief refresher or introduction to general relativity. The core concept of general relativity is that there's no such thing as space or time in and of themselves. They are two aspects of the same object, space-time. In general relativity, space-time is in the form of a Riemannian manifold, which is equipped with a metric tensor. The metric is determined by something called the Einstein field equations, which are some partial differential equations which describe how mass and energy change the metric. There is a feedback loop. Mass energy sculpts space-time, and space-time tells mass energy how to move. As a result, this ends up governing the shape of the universe. The acceleration due to gravity at a given point in general relativity is given by how curved spacetime is at that point. In turn, the spacetime curvature at a point is given by the metric tensor at that point. Thus, the gravitational acceleration is ultimately derived from the distribution of mass energy. As a terminological note, internally straight lines through spacetime will just be called geodesics. Okay, so black holes are simply regions of spacetime which restrict all geodesics passing through them to remain in them. And no, we are not going to be considering like Kerr spacetimes. I'm not going down that wormhole, and this time that pun was intended. Black holes are not physical objects in the sense of black holes are not physical objects in the sense of consisting of matter which you can like pick up and hold, except for perhaps the singularity. It's merely a region of spacetime. Okay, now, energy is required to store information in the physical world. I don't mean anything fancy like Landauer's limit, but rather that information has to exist in some physically manifested way. That takes energy due to mass energy equivalence. Spacetime becomes more curved at a point the higher the energy density at that point. There's a finite amount of energy you can stuff in a volume of spacetime. When you hit that limit, that volume is by definition a black hole. Since information requires energy to exist in the physical world, and there's a hard limit to the amount of energy you can shove into a volume of spacetime, then there's a hard limit to the amount of information you can put into that volume of spacetime. This is called Bekenstein's bound. That limit is called Bekenstein's bound, given by that formula. Okay, so now we'll take a brief detour into quantum field theory. When you accelerate in a vacuum, you experience immersion into a thermal bath due to something called the Unruh effect. As you can see, the experienced temperature is proportional to the acceleration. Now, let's combine general relativity and quantum field theory. Recall the equivalence principle of general relativity. Acceleration due to gravity, not due to general relativity. Just recall the equivalence principle. Acceleration due to gravity is indistinguishable from acceleration caused by other forces. Stronger gravity, that is, stronger curvature of space-time, results in higher acceleration. Thus, thanks to the Unruh effect, the more strongly curved space-time is at a point, the hotter it is. As the Unruh effect results in curved space-time having an effective temperature, it will do that what all things with thermal energy do, emit black body radiation, just like the thermal radiation of more corporeal objects. Thus, the space-time itself behaves as a black body and therefore emits thermal radiation. As higher temperatures result in more black body radiation and stronger curvature results in higher temperatures, the more curved spacetime is, the more thermal radiation it emits. We call this radiation Hawking radiation. So just, okay, I'm not going to have time to go into this, so just skip this. All right, so with that in mind, let's move on to the actual content. We will consider small, compact agents, that is, agents who are sufficiently dense that they're almost at the point where they collapse into a black hole, which is called their Schwarzschild radius. So this is a cross-sectional diagram of the curvature of space-time in and near a compact object. The transition point is at where the pink meets the blue. If it was a black hole, that would be the event horizon. As the spatial curvature at a point increases, the externally viewed time for information to propagate across that point dramatically increases without bound. The average curvature inside the agent increases as it approaches its Schwarzschild radius. Thus, the average time for information to propagate also increases. Viewed internally, it appears that your brain becomes stretched out to an arbitrary size. Thus, the latency for things like memory recall increases without bound the denser you become. Okay, so something else. Thanks to Hawking radiation, small compact agents are actually luminous. They glow. The more compact and the smaller the object, the more luminous it is. This is just talking about the thermal radiation emitted by the Unruh effect, by the way, not including like any deliberate signaling or like any other methods of emission. For reference, a 1 kilogram black hole is bright, really, really bright, as in comparable to some of the brightest stars known to exist, bright. As a 1 kilogram agent approaches its Schwarzschild radius, its luminosity sorry, I should have said earlier, a 1 kilogram black hole is bright. Anyway, as a 1 kilogram agent approaches its Schwarzschild radius, its luminosity similarly becomes ridiculously bright. Okay, I did have time. I'll go back to that. So a linear channel is something which propagates a continuous time signal. The noise spectrum of the channel determines the difficulty of communication. So think of static on a given radio band, and higher noise requires more powerful signal transmission to compensate. So at long wavelengths, it is a valid approximation to consider the Hawking radiation to be sufficiently spectrally uniform over a given band of frequencies. In engineering terms, we can consider the Hawking radiation to be what's called additive white Gaussian noise. Additive because its contribution to the noise environment is purely additive. White because the spectral power density of the noise is effectively uniform. Or flat Gaussian because the Fourier transform of a constant spectrum is a Gaussian curve. No, it's not. Of a bounded spectrum is a Gaussian curve. And noise, because it's not containing any information that we are deliberately trying to transmit. As there is more noise power, you thus need to compensate with higher signal power. This means you have to have more energy reserves in the first place to maintain a given signal-to-noise ratio. In turn, if you want to avoid collapsing into a black hole, you have to sacrifice computational energy. Alternatively, or additionally, you have to sacrifice energy used for memory storage. So let's quickly consider the environmental concerns around being compact. Due to the enormous luminosity, if it's lucky, the environment nearby will be quickly vaporized to a plasma. The plasma will be pushed away by the extraordinarily high photon pressure. What's more, if the agent can sustain its energy requirements, this happens continuously. For smaller agents with a mass of, say, 50 grams, it would be like a smallish supernova happening constantly. For those objects which are not granted the mercy of swift disintegration, they have another problem to deal with: being blasted by hard gamma rays. A lot of them. For those unlucky enough to be in this regime, you'll maintain some semblance of structural integrity for a while, but a significant amount of your atoms will be transmuted into radioactive isotopes. Further away, your molecules will quickly be ripped apart, and yeah, you'll have severe radiation poisoning. Therefore, the physical embodiment of a task must be rather robust to survive long enough to enable task completion. But just how quickly does our agent radiate itself into oblivion? Well, a 1 kilogram compact agent will evaporate in approximately 50 attoseconds, or 50 quintillionths of a second. For reference, for a nice teal color light of around 500 nanometers, the light will travel approximately 1% of its wavelength, which is ridiculously small. Therefore, if we want the agent to survive, we have to supply the agent with food at a rate of 1 kilogram per 50 attoseconds. That's about twice the carbon content of all life on Earth per second. And as you get more mass, you radiate less, thus you need to replenish less, and existing is easier. So, onto some tasks. What are tasks? Well, for our purposes, tasks are specified as Turing machines. Given an input string, return an output string, which is accepted by the task Turing machine. Interactive tasks can be thought of as sequences of primitive tasks, along with a notion of monotonic time. But we'll only look at primitive tasks. So what are some difficulty measures for tasks or Turing machines? Well, there's, let's say, the algorithmic probability of the task Turing machine, also known as the Shannon probability, Solomonov probability. There's also the computational complexity of the task Turing machine. But we will, of course, be using the Kolmogorov complexity. So an environment must contain the agent, the task specification, and the output eventually. All of these must be physically embodied if this is a physical task. Okay, so now we say we have some task we wish for an agent to complete. We denote by new here the Kolmogorov complexity of the task, conditionalized over the instance-specific input. We'll call this the state difficulty length, but we'll never call it that again. For this task to exist in this environment, the agent, for this task to exist in the environment alongside the agent, the environment must be in a volume bounded by this fun inequality. If it meets this equality, then it will be a black hole. But yeah, that's a hard physical limit that is given purely by the laws of physics. I don't have time for this. I have negative 22 seconds left. Okay, so some quick observations. Firstly, it's readily apparent that it is critical to keep track of your mass energy and how it is spent. Your very existence depends on how much you interact with the world, how much you think, what you think about, and so on. You are forever on the precipice of a very messy and loud death. In particular, this manifests as a particularly spicy version of the exploration versus exploitation trade-off. Too much exploration, well, learning, and you observe and you gather too much information, and you collapse into a black hole. Too little exploration, and you might accidentally thermalize yourself into a dense plasma by starvation. This may or may not be desirable, depending on mood. Further, most thoughts are simply too big to ponder. This means that there are only a finite amount of things that are allowable. There's only a finite amount of thoughts there's a hard sentence. There's only a finite amount of thoughts that are allowable at any one time, unless we don't care about collapsing into a black hole. This also brings up the question of little compression bombs. If some thought is parameterized in such a way that its fixed point isn't finitely representable or more accurately representable within your given volume, then it seems to follow that there's always a method to collapse into a black hole by mere contemplation. Finally, due to the environmental effects, anyone who ensures that a compact agent is fed for any non-trivial amount of time in an inhabited solar system commits a cosmic sin and is to be shunned. So yeah, the exact numerical results, which I kind of didn't show too many of numerically, but yeah, these exact results aren't necessarily important here. Because, well, for one thing, a true theory of quantum gravity will likely adjust many or most of them and invalidate completely some of them. But like I said, that's not necessarily important. It's the general approach. Examining physical effects resulting from computation and information being existing in our physical universe is the thing to take away from this. So what can we use this for, like, practically? I don't know. It's fun to think about. If your theory of consciousness doesn't emit a physical embedding which reproduces these results, then either it cannot be a computational theory, or it cannot be a physicalist theory, or one of my assumptions is wrong. And instead of using Kolmogorov complexity, we could use algorithmic probability in its place to derive a similar result to the volume the volume required for the environment, but then everything becomes an expected value, and you can rule stuff out, I guess. So yeah, that's it.